Right now, as you watch this, every star in the night sky is burning through its fuel, every galaxy is drifting further from its neighbors, and the cold empty void between them grows larger with each passing second. This isn't speculation. This isn't philosophy. This is what the laws of physics tell us is happening, has been happening for nearly 14 billion years, and will continue happening long after Earth, the Sun, and everything we've ever known has vanished. But here's what keeps cosmologists awake at night: we don't actually know how it ends. We've mapped the cosmic microwave background radiation, the afterglow of creation itself. We've measured the expansion rate of space with extraordinary precision. We've detected gravitational waves rippling through the fabric of spacetime from colliding black holes billions of light years away. And yet, when we ask the simplest question a child might ask, what happens at the end? We find ourselves staring into a profound mystery. There are 5 possible endings to our cosmic story, and each one is more disturbing than the last. Let's start with what we know for certain. In 1929, Edwin Hubble made a discovery that would forever change our understanding of reality. By studying the light from distant galaxies, he noticed something strange. The light was shifted toward the red end of the spectrum, stretched out, elongated. This could only mean one thing: those galaxies were moving away from us. And not just some of them, all of them. Every galaxy in every direction was receding, and the further away they were, the faster they seemed to be fleeing. The universe was expanding. Now, this wasn't entirely unexpected. Einstein's equations of general relativity, published in 1915, had already predicted that the universe couldn't be static. Space itself had to be either expanding or contracting. Einstein himself was so disturbed by this implication that he introduced a fudge factor into his equations, a cosmological constant, specifically designed to hold the universe still. He later called it his greatest blunder. But Hubble's observations proved that the universe was indeed in motion. And if you run that motion backward, like rewinding a cosmic film, you arrive at an inescapable conclusion. At some point in the distant past, everything, all matter, all energy, all of space itself, was compressed into an unimaginably small, hot, dense point. And then it exploded outward in what we now call the Big Bang. For decades after Hubble's discovery, cosmologists assumed they knew how this story would end. The universe was expanding, yes, but surely gravity would eventually slow that expansion down. All the matter in the cosmos was pulling on all the other matter, creating a cosmic drag that would gradually bring everything to a halt. The only question was whether there was enough matter to actually reverse the expansion or merely slow it to a crawl. If there was enough matter, gravity would eventually win. The expansion would stop, reverse, and everything would come crashing back together in a mirror image of the Big Bang, the Big Crunch. The entire universe compressed back into that primordial point, perhaps to explode outward again in an endless cycle of creation and destruction. If there wasn't quite enough matter, the expansion would slow but never quite stop. The universe would coast to a gentle halt, frozen in place for eternity, stars slowly burning out one by one until only darkness remained. Either way, the future seemed predictable. Gravity was in control. The universe would either collapse or coast. Those were the only options physics allowed. And then, in 1998, everything changed. two teams of astronomers were independently studying a particular type of stellar explosion called a Type Ia supernova. These explosions are special because they all release almost exactly the same amount of light. They're like cosmic standard candles. If you know how bright something actually is, and you measure how bright it appears, you can calculate exactly how far away it is. By finding these supernovae in distant galaxies, the teams hoped to measure how much the expansion of the universe had slowed over cosmic time. They expected to find that distant supernovae, whose light had traveled billions of years to reach us, would appear slightly brighter than predicted, indicating that the universe was expanding more slowly in the past. What they found was the opposite. The distant supernovae were dimmer than expected. The universe wasn't slowing down. It was speeding up. The expansion was accelerating. This made absolutely no sense. It was as if you threw a ball into the air and instead of falling back down, it flew upward faster and faster, defying gravity entirely. The teams checked their data, rechecked their calculations, looked for errors in their instruments. There were none. The universe was genuinely accelerating, and no one had any idea why. To account for this acceleration, physicists introduced a new term into their equations, a term that looked suspiciously like Einstein's discarded cosmological constant. They called it dark energy, not because they understood what it was, but because they had no idea what it was. Dark energy is the name we give to our ignorance. It's a placeholder for something that makes up roughly 68% of everything that exists, yet remains completely invisible, undetectable by any instrument, and fundamentally inexplicable. All we know is what dark energy does: it pushes space apart. It creates new space between galaxies, not by moving the galaxies through space, but by creating more space itself. And as space expands, there's more space to create more expansion, which creates more space, in a runaway feedback loop that has been accelerating for the past 5 billion years and shows no signs of stopping. This discovery forced cosmologists to completely rewrite the ending of the cosmic story. And the new ending is far stranger than anyone had imagined. If dark energy continues to push space apart at its current rate, the universe is headed toward what's called the Big Freeze, or sometimes the heat death. Here's how it unfolds. As space expands, galaxies drift further and further apart. Right now, the nearest large galaxy to us, Andromeda, is actually moving toward the Milky Way. In about 4.5 billion years, the two galaxies will collide and merge into a single giant elliptical galaxy that astronomers have playfully named Milkomeda. But that will be one of the last great cosmic events our descendants, if any exist, will ever witness. Because while Andromeda is close enough that gravity still dominates, everything else is being carried away by the expansion of space. The Virgo cluster, about 50 million light-years away, is receding. The great cosmic web of galaxy superclusters that stretches across the observable universe is being stretched thinner and thinner. In about 100 billion years, every galaxy beyond our local group will have receded so far that its light will no longer be able to reach us. The expansion of space will carry those galaxies beyond a cosmic horizon, a point of no return from which no signal, no matter how fast it travels, can ever reach us. From the perspective of any observer in Milkomeda, the universe will appear to contain only one galaxy, floating alone in an infinite dark void. The billions of other galaxies will simply disappear, erased from the observable universe not by destruction, but by distance. But the real horror of the Big Freeze lies not in the loneliness of an isolated galaxy, but in what happens afterward. Stars die. This is an inescapable fact of stellar physics. Stars fuse hydrogen into helium, helium into carbon, carbon into heavier elements, releasing energy at each step until they hit iron. Iron fusion consumes more energy than it releases, and at that point, the star's fuel runs out. Depending on its mass, the star will end its life as a white dwarf, a neutron star, or a black hole. The universe is currently about 14 billion years old. The most massive stars burn through their fuel in just a few million years. The smallest red dwarf stars, however, are so parsimonious with their hydrogen that they can keep burning for trillions of years, 100 times longer than the current age of the universe. But eventually, even they will die. In about 100 trillion years, that's a 1 followed by 14 zeros, the last star in the universe will exhaust its fuel and flicker out. The stellar era of cosmic history, the age of light and warmth and the possibility of life, will be over. What remains will be a universe of stellar corpses, white dwarfs slowly cooling, neutron stars spinning down, and black holes drifting through the darkness. But even these remnants won't last forever. White dwarfs, those dense cores of dead sun-like stars, will gradually radiate away their remaining heat into the void. Over timescales so long they make the age of the current universe seem like the blink of an eye, we're talking 10 to the power of 15 years, 10 to the power of 20 years, they will cool to the temperature of the cosmic background, becoming invisible black dwarfs that emit nothing and absorb nothing and simply exist in the darkness. Neutron stars will suffer a similar fate, their incredible rotation slowing, their magnetic fields weakening, their surface cooling until they too become cold, dead husks. And the black holes? The black holes will evaporate. This seems impossible. Black holes are the ultimate gravitational traps, regions of space where gravity is so strong that nothing, not even light, can escape. How can something that traps everything possibly evaporate? The answer lies in quantum mechanics, specifically in a phenomenon discovered by Stephen Hawking in 1974. Empty space isn't actually empty. At the quantum level, pairs of virtual particles are constantly popping into existence and annihilating each other, appearing and disappearing so quickly that they don't violate conservation of energy. But near the event horizon of a black hole, something strange can happen. One particle of a virtual pair can fall into the black hole while its partner escapes. To an outside observer, the black hole appears to emit a steady stream of radiation, Hawking radiation. This radiation carries energy, and that energy has to come from somewhere. It comes from the black hole's mass. Bit by bit, particle by particle, over unimaginable stretches of time, black holes slowly shrink and evaporate. For a stellar mass black hole, this process takes about 10 to the power of 67 years. For the supermassive black holes at the centers of galaxies, monsters containing billions of solar masses, it takes 10 to the power of 100 years, a googol years. But eventually, every black hole in the universe will evaporate, ending their lives in a final burst of Hawking radiation. And then nothing. A universe of diffuse radiation, slowly cooling, expanding forever into an infinite void. No stars. No planets. No black holes. No structures of any kind. Just an endless, formless sea of particles, each one isolated from every other by vast stretches of empty space, forever expanding, forever cooling, approaching but never quite reaching absolute zero. This is the heat death of the universe. Not a dramatic explosion or collapse, but a slow, inexorable fade to black. The ultimate triumph of entropy, the second law of thermodynamics made manifest on a cosmic scale. All the energy in the universe, once concentrated in stars and galaxies and living things, spread so thin across such immense volumes that nothing interesting can ever happen again. It is, by any measure, a profoundly depressing vision of the future. But it may not be the true ending. Because dark energy might have other plans. Remember, we don't actually know what dark energy is. We've measured its effects with extraordinary precision, but its underlying nature remains completely mysterious. In our current models, dark energy is constant. It exerts the same repulsive pressure per unit volume of space now as it did billions of years ago and will continue to do so billions of years from now. But what if that's wrong? Some theoretical models suggest that dark energy might not be constant. It might be changing over time. Specifically, it might be increasing. If dark energy grows stronger as the universe ages, the expansion won't just continue, it will accelerate faster and faster, eventually tearing apart everything in existence. This scenario is called the Big Rip. In a Big Rip scenario, the acceleration of space becomes so extreme that it eventually overwhelms all other forces. First, the gravitational attraction that holds galaxy clusters together. Then the gravity that holds individual galaxies together. Then the gravity that holds solar systems together. Then the electromagnetic forces that hold molecules together. Then the strong nuclear force that holds atoms together. In the final fractions of a second before the Big Rip, space expands so rapidly that even subatomic particles are torn apart, the very fabric of matter shredded by the expansion of spacetime itself. Current observations suggest that dark energy is constant, which would rule out the Big Rip. But our measurements aren't precise enough to be certain. The Big Rip remains a genuine possibility, a cosmic doomsday lurking within the error bars of our data. And there's an even stranger possibility, one that would reverse the entire story. What if dark energy isn't constant, but is actually weakening over time? What if, at some point in the distant future, it fades away entirely or even reverses sign, switching from repulsion to attraction? This would bring us back to the scenario cosmologists considered before 1998, a universe where gravity eventually wins. The expansion would slow, stop, and reverse. Galaxies would begin falling toward each other, slowly at first, then faster and faster. The cosmic microwave background radiation, now a faint whisper of microwaves, would blue shift as space contracted, growing hotter and more intense. Galaxies would merge into a single cosmic mass. Stars would be ripped apart by tidal forces. And in the final moments, all of space, all of time, all of matter and energy would compress back into an infinitely dense point. The Big Crunch. This scenario has fallen out of favor since the discovery of dark energy, but it hasn't been entirely ruled out. We simply don't know enough about dark energy's long-term behavior to say for certain that it won't weaken or reverse. And here's where things get really interesting. What happens after the Big Crunch? In classical physics, the Big Crunch would be the end. A singularity of infinite density and zero volume, where the laws of physics as we understand them break down completely. The end of time itself. But some cosmologists have proposed a more hopeful possibility, the Big Bounce. In this scenario, the universe doesn't actually reach a singularity. Instead, some new physics kicks in at extremely high densities, creating a repulsive force that halts the collapse and triggers a new expansion. The Big Crunch becomes a big bounce, and a new universe emerges from the ashes of the old one. This idea has deep roots in certain approaches to quantum gravity, particularly a theory called loop quantum cosmology. In loop quantum cosmology, space itself is quantized. It comes in discrete units, like pixels on a screen. When the universe contracts to the point where these quantum effects become important, the smooth continuum of classical spacetime gives way to a granular structure that resists further compression. The universe bounces. If this is correct, our Big Bang might not have been the beginning of everything. It might have been a big bounce, the rebirth of a previous universe that collapsed. And the cycle might repeat indefinitely, universe after universe, bounce after bounce, an eternal cosmic phoenix rising from its own ashes. But the Big Bounce is just one version of an even grander idea, the cyclic universe. Cyclic cosmologies have been proposed in many different forms. In the 1930s, Richard Tolman explored the idea of an oscillating universe, where expansion and contraction alternate forever. But Tolman's model had a fatal flaw, the second law of thermodynamics. Each cycle would produce entropy, which would carry over to the next cycle, causing each successive universe to be larger and longer-lived than the previous one. Run the clock backward, and you eventually reach a first cycle, a beginning, which defeats the whole purpose of a cyclic model. Modern cyclic theories try to avoid this problem in various clever ways. One of the most developed is the ekpyrotic model, proposed by Paul Steinhardt and Neil Turok in the early 2000s. In this model, our universe is a three-dimensional membrane, or brane, floating in a higher dimensional space. Periodically, our brane collides with another parallel brane, and these collisions trigger what we perceive as big bangs. The universe expands, evolves, and eventually empties out, only to collide again with the other brane and restart the cycle. In the ekpyrotic model, entropy isn't a problem because the universe has essentially infinite time to dilute its entropy between cycles. Each collision resets local conditions without violating thermodynamics. Another cyclic model, conformal cyclic cosmology, was proposed by Roger Penrose. In Penrose's vision, the far future of our universe, after all matter has decayed and only massless particles remain, becomes mathematically indistinguishable from the hot, dense state of a new Big Bang. The end becomes the beginning, and the cycle continues without the need for a bounce or collision. These cyclic models are highly speculative, and none of them have strong observational support. But they're not ruled out either. And they offer something that the Big Freeze or Big Rip cannot, a universe without an ultimate ending, a cosmos that goes on forever in some form. So which ending is correct? The honest answer is that we don't know. And we may never know. The fate of the universe depends on the nature of dark energy, and despite decades of effort, we still have no idea what dark energy actually is. Is it a cosmological constant, a fixed property of spacetime itself? Is it a dynamic field that changes over time? Is it an illusion, a sign that our theory of gravity is incomplete on cosmic scales? Each possibility leads to a different ending. It also depends on questions of physics we haven't yet answered. What happens at the Planck scale, where quantum effects and gravity become equally important? Is there a theory of quantum gravity that would modify our predictions for the ultimate fate of the cosmos? Does the universe have additional dimensions beyond the three of space and one of time that we experience? These questions remain open, and their answers could radically change our cosmic forecast. And there are even deeper uncertainties that touch on philosophy as much as physics. Is our universe all that exists? Or is it one of many universes in a vast multiverse, perhaps spawned by eternal inflation, perhaps part of an infinite landscape of string theory vacua? If the multiverse is real, then even the death of our particular universe might not matter in any ultimate sense. Other universes would continue, perhaps hosting other forms of life, other kinds of consciousness, other questions about ultimate endings. What does it mean for the universe to end, anyway? If the heat death arrives and nothing interesting ever happens again, is that really an ending, or just an eternal unchanging existence? Is a universe without observers, without anyone to experience it, even real in any meaningful sense? These are questions that physics alone cannot answer. And there's one more question, perhaps the most important of all: what does any of this mean for us? The timescales we've been discussing are almost incomprehensibly vast. The last star will burn out in 100 trillion years. Black holes will evaporate in googol years. These numbers are so large that they lose all human meaning. Our entire species has existed for perhaps 300,000 years. Recorded human history spans maybe 5,000. The gap between now and the Big Freeze is to the age of human civilization as the age of human civilization is to the blink of an eye. On these timescales, everything we know, everything we've built, every work of art and act of love and scientific discovery will be utterly forgotten, erased not by violence or catastrophe but simply by the passage of time. The universe doesn't care about us. It isn't hostile, it's simply indifferent, operating according to physical laws that have no preference for human survival or meaning. This could be cause for despair. But it could also be cause for something else. Because right now, in this brief cosmic moment when the universe is young and stars are plentiful and complexity is possible, we exist. Against astronomical odds, on a small rocky planet orbiting an ordinary star in the suburbs of an unremarkable galaxy, matter has organized itself into beings that can look up at the night sky and ask where it all came from and where it's all going. We are the universe becoming aware of itself, and that is remarkable regardless of how long it lasts. The physicist Sean Carroll has written about what he calls poetic naturalism, the idea that even in a universe governed by blind physical laws, without inherent purpose or meaning, we can create our own meaning. The story of the cosmos, from the Big Bang to the Big Freeze, is our story. We are made of star stuff, as Carl Sagan famously said, and that star stuff has somehow learned to contemplate its own existence. Maybe the universe will end in ice, slowly fading to black over timescales that dwarf imagination. Maybe it will end in fire, torn apart by accelerating expansion or collapse back into the furnace of a new Big Bang. Maybe it will cycle forever, or branch into infinite alternatives, or do something we haven't yet imagined? We don't know. And in a way, that's the most wonderful thing about it. The mystery remains, inviting us to keep looking up, keep asking questions, keep pushing the boundaries of what we understand. The universe has been around for nearly 14 billion years and has trillions more ahead of it, at minimum. It has produced galaxies and stars and planets and, at least once, life capable of wondering about its fate. Whatever ending awaits, the story of the cosmos is still being written. And for now, in this narrow window of cosmic time when such things are possible, we get to be part of the telling. The stars are dying. The void is growing. And we are here to witness it, these tiny sparks of consciousness in an endless dark ocean, trying to understand. Perhaps that's enough. Perhaps that's everything.